Okay, good afternoon, everyone. Professor Bond, Professor Efstathiou, esteemed colleagues, students, and guests. Welcome to the Shaw Prize in Astronomy, Shaw Prize Lecture in Astronomy 2025. I am Professor Man Hoi Lee of the Department of Earth and Planetary Sciences and the Department of Physics at the University of Hong Kong. It is a great honor to stand before you today as we gather to celebrate the Shaw Prize, honoring scientists whose breakthroughs have advanced human knowledge across many fields. And I'm delighted to introduce the 2025 laureates in astronomy and our speakers today, Professor John Richard Bond from the University of Toronto and Professor George Efstathiou from the University of Cambridge. They are renowned for their pioneering work in cosmology and in particular on the cosmic microwave background, the faint lights that's left over from the dawn of the universe. Their ideas, later confirmed by a new generation of experiments, have enabled us to measure the age, shape, and contents of the cosmos with extraordinary precision. Thanks to their vision, cosmology has become one of the most exciting and exact sciences of our time. Professor John Richard Bond, or Dick Bond, as everyone refers to him, is university professor at the University of Toronto. His theoretical work ranges from ultra-early to ultra-late universe, with major contributions to our understanding of dark matter and dark energy, cosmic inflation, and the cosmic web of large-scale structure. He is best known for developing the study of fluctuations in the cosmic microwave background into a precise tool for probing the cosmos. On a personal note, I actually first met Dick when I was an undergraduate student at the University of Toronto, and he just arrived at the newly founded Canadian Institute for Theoretical Astrophysics. And I got to know him much better when I was a postdoc there at CETA. As the director of CETA for a decade, he helped to secure Canada's place at the forefront of astrophysics and cosmology. His contributions has been widely recognized with numerous honors, including the Order of Canada, the Gruber Prize in Cosmology, and the Killam Prize in Natural Sciences. Professor George Efstathiou is Emeritus Professor of Astrophysics at the University of Cambridge. He is renowned for his wide-ranging contributions to both theoretical and observational cosmology, and has contributed to studies of large-scale structure in the universe, galaxy formation, dark energy, and the cosmic microwave background. Over his career, he has held major appointments, such as the Civilian Chair of Astronomy at Oxford University, and he was the first director of the Kavli Institute for Cosmology at Cambridge University. He has also been widely honored in the astrophysics community, having received awards including the Gruber Prize in Cosmology, jointly with Mark Davis, Carlos Frank, and Simon White, and the gold medal of the Royal Astronomical Society. He is also a fellow of the Royal Society. I have not had the pleasure to meet Professor Efstathiou until this week, but I've actually crossed paths with him scientifically many years ago when I was actually working on a paper on gravitational lensing with a collaborator from large-scale structure. He actually kindly provided us with the data from a numerical simulations, which was from one of the classic paper by White, Davis, Frank, and Efstathiou. Here at HKU, the Department of Physics and the Department of Earth and Planetary Sciences and the Laboratory for Space Research have continued to make important contributions across astronomy and astrophysics, from planetary exploration and lunar sample studies to involvement in major national and international space missions, to breakthroughs in understanding exoplanets, neutron stars, black holes, and the nature of dark matter. Our departments and research units are advancing the frontiers of knowledge. With strong support from government initiatives and competitive funding, we are also helping to strengthen Hong Kong's role in the national and global space and astrophysics community. Today, these achievements demonstrate the breadth and depth of our faculty's contribution to astrophysics, from probing the possibility of life beyond Earth to exploring the most extreme phenomena of the cosmos. I'm happy to say that the next step in our efforts to establish HKU as an international center of research excellence in astronomy and astrophysics will be taken on November 3rd with the inauguration of the Hong Kong Institute of Astronomy and Astrophysics. And now, it is my pleasure to invite the 2025 Shaw Prize laureates in astronomy, Professor George Efstathiou and John Richard Bond, to deliver their lecture, From the First Light to the Cosmic Web. Professor Efstathiou, please begin.
Okay, well, thank you for the introduction. So I'm going to give the talk in two parts, not quite equal parts. The first one is going to be discussing how we got to the lambda CDM cosmology and putting the work that Dick and I did in context with what we know about this model. And then the second part, I'll focus on whether there's any indication observationally that the model might need to be refined. So to start, I mark the birth of modern cosmology with the discovery of the cosmic microwave background in 1965, and this is Penzias and Wilson, who discovered the CMB with this radio telescope. And what they discovered, of course, was the remnant radiation from a hot phase of the universe. And as the universe has expanded, it's cooled down, and it now has a temperature of 2.7 Kelvin. So as soon as this discovery was made, experimentalists started a search for temperature fluctuations. Is the temperature 2.7 K in every direction on the sky? So the search for anisotropies began, and theorists also knew that there should be temperature fluctuations in the cosmic microwave background because our universe is not perfectly smooth and homogeneous today. We see structure in the universe, and this shows a space-time diagram. So we're at the center here, and then this shows the paths of photons that travel towards us. And because the universe is expanding, as we look at greater distances, we see the universe at an earlier stage of evolution. And because of the existence of the cosmic microwave background, the further back in time we look, the hotter the universe is. And at a redshift of 1,000, so this is when the universe was 380,000 years old, the universe is too hot to have neutral hydrogen. So hydrogen becomes ionized into its constituent electrons and protons. And at that point, photons are tightly coupled to the electrons via Thomson scattering. So the universe becomes opaque. So when we look at an image of the cosmic microwave background, we see a picture of the universe as it was at the time that electrons and protons combined to make neutral hydrogen. So this shows the path of a photon at very early times. The photon is tightly coupled to the electrons via Thomson scattering, so it has a short mean-free path. Then the universe cools down, and then the photons travel towards us almost in straight lines. In fact, they don't follow exactly straight lines because intervening matter causes a deflection via gravitational lensing, and that in itself is a very powerful way of testing the evolution of the universe. So if there's an underdensity at what we call the last scattering surface at this time, then a photon will be blue shifted as it comes towards us, and if there's an overdensity, it will be red shifted as it comes towards us. So if we look in different directions of the sky, fluctuations in the gravitational potential at a redshift of 1,000 will cause temperature fluctuations. And then you can go further from from observations, if we look at the dynamics of clusters of galaxies, then we see the typical galaxy motions are about 1,000 kilometers per second in a cluster of galaxies. And so the temperature, if the fluctuations are scale invariant, if the amplitude is independent of scale, on these large scales, we'd expect to see temperature differences in the microwave background that's of order V over C squared. So about 10 to the minus 5, about 1,000%. So that's all straightforward, and that was understood at the time that the microwave background itself was discovered. So, but 10 to the minus 5 is a very small number. And so, as we'll see, it took a long, long time before the temperature fluctuations were discovered. But but they were expected theoretically. So this is Campbell Hall, which has now been demolished at Berkeley. So this is where the astronomy department was on the top 2 floors of this building. And that's when I first met Dick in 1979. And here we are at around that age. You see, I'm the handsome one. So and we were working on different things back then. But that's when we first met. And what happened, I mean, memory can be deceptive, but in my recollection, what happened was that I was on the phone to Mark Davis, who's one of our collaborators and great friends, and he told me of a Russian experiment that had claimed to detect a mass of the electron neutrino of about 30 electron volts. And that sort of mass would be enough to make the dark matter in the universe. You could make the dark matter in the universe out of neutrinos. So I went into Dick Sockers. Dick was a neutrino expert, and I said, have you heard about this? And he hadn't. And then a few phone calls later, we had more information, and we started to think about how structure would form in a universe in which the dark matter was made up of material that's different from baryonic material that makes us up, so some sort of weakly interacting particle. So we started working on massive neutrinos. That model didn't work, and Carlos and Simon also did numerical simulations to show that this type of model didn't work. But it was also clear that if there was a particle that was much more massive than a neutrino, some neutrino-like particle, then you could make a viable model of structure formation. So that was the situation. But when we first started doing this type of work, investigating non-baryonic dark matter, we didn't have any real clue about the initial conditions of the fluctuations. How did the fluctuations get generated, and what sort of properties did those fluctuations have? Then, for me, this meeting, held in Cambridge in 1982, is the most important scientific meeting that I've ever attended. So I was a postdoc in Cambridge at this time, and what happened was people came to this meeting with different calculations for how quantum fluctuations in the early universe could be inflated in scale during an inflationary phase where the universe expands faster than the speed of light. And the idea was that these quantum fluctuations could be inflated in scale and become classical fluctuations. And people came to this meeting with different calculations and different answers. So some people claimed that this was a nice mechanism, but the amplitude was too small to be of any relevance. And others came saying that the amplitude was too big and made inflation, so was an argument against an inflationary phase in the early universe. And what happened was that this problem was solved in real time in the 2 weeks of this meeting. And so at the end of that meeting, a theory of the generation of quantum of fluctuations in the early universe emerged. And so that meant that we could really start to calculate and try and construct a complete theory of structure formation from an inflationary phase, making assumptions about the nature of dark matter right the way through to the formation of nonlinear structure in the present day. And so, here's the basic cartoon idea that you start off with a tiny little region of the universe that's maybe 10 to the minus 33 centimeters or whatever. The universe goes through an inflationary phase and quantum fluctuations get inflated in scale. And to do that, the universe has to be full of funny stuff that has a negative pressure. But developments in field theory meant that, how that could happen, at least in a schematic form, was understood. So Dick and I are good friends. I'm still the handsome one. And we start. He's going to get me back when he gives his talk. Okay. So we started on this project to calculate the temperature fluctuations, and this is an example of the type of calculation that we were doing. This shows the power spectrum expected of the cosmic microwave background fluctuations. This is telling you the amplitude of the fluctuations as a function of angular scale on the sky. And calculations that we did predicted power spectra that looked like this. And the basic structure of these things is quite simple to understand, because at very early times, the electrons and photons are tightly coupled. And so this the baryon photon fluid fluctuations produce sound waves, and so what you see is oscillations in the temperature fluctuations that are generated by the oscillations of sound waves before the universe became neutral. And the distance, this scale here, corresponds to about 2 degrees on the sky, and that tells you the maximum distance that a sound wave can travel from the beginning of the universe to the time that the universe becomes neutral, and we see the anisotropies on the sky. And so that's something that we can calculate, and then this becomes a geometric test, a test of the geometry, the position of this acoustic peak. The fluctuations here are caused by the gravitational potential wells on large scales. And there are two sources of fluctuations shown here. This solid line is caused by the fluctuations that form structure that we see today. But there's also the possibility that you can generate temperature anisotropies in the microwave background from gravitational waves during an inflationary phase. That has not been detected yet. Okay, so we haven't seen evidence of gravitational waves generated during inflation. The positions and amplitude of these peaks acts as a sort of cosmic fingerprint that if you make accurate measurements, you can only match the observations if you choose the parameters of the universe very precisely. This is the value of the Hubble constant and the baryon density. So these are sort of funny parameters compared to what we now know. But you can vary the parameters and it varies the shape. And that means that if you make accurate measurements of the cosmic microwave background anisotropies, then you can test the parameters of the universe. You can test for the geometry and the matter composition and the parameters of the fluctuations in the early universe. So with this, we also generated realizations. This is what we said observers should see in a 10 degree by 10 degree patch of the sky. So this type of realization is now routine, but back when we first produced these, people didn't really know what we were showing them. Anyway, so we could make these predictions for the temperature fluctuations, but there were no measurements at the time that we did this work. So the fluctuations themselves were discovered in 1992 by NASA's COBE satellite, and this is the map that COBE produced. And the resolution of this map is around 7 degrees. So you don't see that first big peak in the power spectrum. So what you're seeing here are the effects of curvature fluctuations generated during inflation, so the gravitational effects on the cosmic microwave background. And the amplitude was around 1,000%. Okay, so this type of map, the blue regions show where the temperature is slightly less than the average, and these green regions where it's slightly hotter than average. So this was important, but these measurements themselves were not good enough to test theories of structure formation. So we had another arm of work using numerical simulations. So this is work that was done with Simon, who's sitting there, with Carlos. So this is Simon, young Carlos, and Mark Davis, who set me on the path with his phone call on looking at weakly interacting massive. So this was before I went through my inflationary phase. So it was quite skinny, and and I am the handsome one here. And the other distinguishing feature is that I'm the only one that doesn't have a moustache. Anyway, this was a great collaboration. Okay, and this is an example of the type of simulation. We're now simulating cold dark matter universes using the calculations that Dick and I did to get the transfer functions, to get the initial conditions that you can set off one of these calculations. So this was, so we thought we were really onto a complete theory of the formation of structure with inflationary initial conditions and then cold dark matter as the dominant constituent to the universe. Now, at around this time, I started a project with my students in Cambridge to map the galaxy distribution on large scales. So the idea here was to get observational information on the large-scale clustering of the galaxy distribution to be able to test and verify this model. So that was the aim. We did the project, and it didn't work. So this, I'm emphasizing this because when you do something and you put a lot of work into something, and then it doesn't agree with your expectation, what do you do? So the answer is that you publish. You have to, okay? And so we published the results, and we also gave a possible explanation that the universe was dominated by a cosmological constant, a form of dark energy. So what we were doing was we were arguing from perturbations that there was another constituent to the universe, a type of dark energy. And that was not widely accepted at the time. And it took another 8 years until people measuring distant supernovae could test the expansion history of our universe directly, geometrically, and found evidence for dynamical dark energy. And that was the birth of the lambda CDM cosmology that we know today. Now, we've been very lucky in this subject because we have had, this is my history of CMB research. Okay? It stops with Planck. Dick will show you what's happened since. And so we had COBE that produced its first results in 1992, WMAP, another NASA satellite that produced results in 2013, and 2003, and the Planck satellite that I was involved in that produced results in its first results in 2013. And so here are the maps. So this is the COBE map that I've already showed you. This is how things improved. Whoops. With WMAP, you can see WMAP had much higher resolution. Now you see the acoustic peaks, the first and the second acoustic peaks in that power spectrum are imprinting a pattern, and the characteristic scale here of these blobs is around 2 degrees. Okay? And then with Planck, that's the resolution. So improved resolution and improved sensitivity. And so the Planck project dominated my life for many years. And it also brought Dick and I back into close collaboration. So this is the launch in 2009. And here we are. This is George Smoot, who sadly died a few weeks ago. Dick and me, and you can see I'm still the handsome one, but you can see the beginnings of my inflationary phase. Okay, so what did Planck do? I'm not going to go into great detail about this because I'll show you one spectacular plot. Here is the power spectrum. The blue points are the Planck measurements. The residuals are shown below. Okay, the difference between the theory, the best fit theory, and the observations. And here is an inflationary universe with inflationary initial conditions and dark matter, weakly interacting dark matter in the form of cold dark matter, and dark energy. And the fit is just perfect, okay? And so that's why the lambda CDM cosmology has become the standard model of structure formation in the universe today. And so here's what we think the composition is. 27% of dark matter, 5% ordinary matter, and dark energy. So we've done a lot of testing of this model using Planck data and other data, and I cannot see any, particularly with CMB data, everything that we've looked at, the polarization properties, the lensing properties, and so on, agree with the expectations of this cosmological model. So that's fine. So do we have a standard model of cosmology? I think the answer is yes, but there are 3 key ingredients to this cosmology. So inflation, which is not understood, the dark matter, which is not understood, and the dark energy, which is certainly not understood. So we've got a very successful model of cosmology, but we don't understand any of the key ingredients, okay? And that's not a happy state, okay? So is it just a fitting function? Some people have said, well, it's just a phenomenological fitting function. And I don't believe that for a moment because going back to this plot, that cannot be an accident. That is telling us some fundamental truth. There's, in my view, clearly some fundamental truth in the lambda CDM cosmology. So I don't think it's just a fitting function. But it's clearly an incomplete theory. So a lot of work now is being directed towards potential problems with the model. So are there any tensions with lambda CDM? And because of the time constraints, I'm not going to be able to go into a lot of detail on this. This is what I've been working on the last few years. I think there's a problem with naturalness, that what we've learned about inflation, because we've not detected gravitational waves, means that the potentials that in inflationary models are unusually flat. And we don't have an explanation for why nature favors these flat potentials. So I think that's a problem that needs further work. To make those models fit, you have to, so the Hubble constant measures the expansion rate of the universe. We get a very accurate measurement of the Hubble tension, assuming this cosmology, and that disagrees with some direct measures of the Hubble parameter, where people have tried to construct a distance ladder locally and trying to measure the Hubble parameter locally. So this has received a lot of publicity, that there's a mismatch. But I think it's important to emphasize that experimenters, different groups, doing essentially the same experiment are getting different answers. And so while that's the situation, I don't think that you can argue that there's definite evidence for a problem with the Hubble constant. Another problem comes from weak gravitational lensing, where surveys of weak gravitational lensing have claimed that the amplitude of the fluctuations is lower than expected in the lambda CDM cosmology. This problem has become known as the S8 tension. I think now the evidence is very strong that there's no problem, that the discrepancy is or discrepancy with past lensing surveys has been caused by systematic errors in the lensing surveys and by people not accounting properly for the way that energy input from galaxy formation alters the matter distribution on small scales. And then there's evolving dark energy. And so I've put some technical things in this talk to antagonize Carlos here, since he's been involved in arguing that there's evidence for evolving dark energy. So this comes from the dark energy spectroscopic instrument. And what this does is it measures the equivalent of the acoustic peak structure in the CMB spectrum, but as seen by the galaxy distribution of galaxies and quasars. And that gives you a standard ruler, a geometric ruler, for which you can test cosmology. So they've done beautiful observations, roughly about 15 million objects now.
40.
Sorry?
40 million.
No, I've only got the public data, which is 3 years, so sorry, it's 15 million, okay? So the claim, so here are some of the measurements. What they do is they measure two geometric distance measures. Okay, so this quantity here, dm, this is the co-moving angular diameter distance, and then this is the Hubble distance. So you can get these two geometric measurements by looking at the distribution of galaxies or quasars along the line of sight and perpendicular to the line of sight. So you get two geometric measurements. And here are the observations. Okay, and DESI DR2 refers to 3 years of data, DESI DR1 refers to 1 year of data, and this is the best fit, and the claim is here is what you'd expect from the Planck CMB measurements, and that there's a discrepancy. So if you just look at these, there doesn't really look to be much of a discrepancy, okay? But I think their interpretation of this plot is wrong, okay? So you're wrong to produce this, okay? And I'll explain. Sorry?
That's data.
The interpretation is wrong, okay? And I'll explain why. These two quantities are very nearly the same thing. You're measuring nearly the same thing. So here's an example of a measurement that they say looks discrepant, okay? So here's DH and here's DM. Now, the errors on these things are set by the geometry of the survey, how many objects you have, what the redshift is, and so on and so on. So you get an ellipse like this. But most of this volume is not accessible to a lambda CDM cosmology. This is just the measurements. But lambda CDM constrains these parameters because they're nearly the same thing. And so in a lambda CDM cosmology, this is for the Planck parameters. Planck tells you that you should lie on a line, actually on a line. And if you notice this, you'll see an interesting thing, that the ellipse points to Planck. That is great, okay, because it's telling you that in the lambda CDM cosmology, all of this is not really important. What's important is how far away you are from this point. Okay, so in these two distance measurements, by the way, RD here is the sound horizon, so it's the physical length that a sound wave can travel. So how long have I got? Plenty of time. So all I have to do is to annoy Carlos. So 10 minutes is plenty of time to do that. So the CMB line, you expect the points to lie on the line. This heavy point here is the best fit from Planck. That looks to be some distance away from here. And then this green point is the best fit that the DESI people have for a lambda CDM cosmology. Okay? So my contribution to this subject was to rotate this. So here are now linear combinations of these two distance measures, where now the Planck results, lambda CDM cosmology, lies on a line here. And this is really useful because if I'm testing the lambda CDM cosmology in terms of this new variable, then the CMB has no error compared to the observations. So I can test how far away we are in this variable with no error from the CMB. So what this becomes, this perpendicular distance, it becomes a measure of geometry. Okay, that's why the points lie, just on in this rotated space on a horizontal line. It becomes a test of geometry, and the CMB is really good at testing geometry. The distance along, how far you are along this line, tells you the matter content of the universe. So what it's actually measuring is the physical density of matter. And so when I'm comparing lambda CDM, what I need to do is to look at the distribution, allow distribution of the data along this direction and along this direction. And that gives me a test of geometry and matter. So now, look at that. This looks a little odd, okay? So the point looks, a little way away from the data. That's based on 1 year's data. Here's how it changes to 3 years' data. Okay, so this is exactly the same redshift range of galaxies, but the difference is between 1 year's set of data and 3 years of data. Now, Carlos, that is brilliant, isn't it? That agrees with lambda CDM. The previous one looked a little discrepant with lambda CDM, but now it agrees beautifully with lambda CDM. So what you were seeing before was a fluctuation. Okay, and then if we look at slightly higher redshifts, that's the 2024 data. You see the perpendicular distance is beautiful agreement with lambda CDM, slight offset in that direction, but bear in mind that in this direction, there's a spread in the measurements from Planck. That's how it changes to 2025. So you can do this exercise, and this is what you get for the perpendicular distance. So this is geometry. Okay, that's the 20, so it's the first year of data, and then this is what happens in 3 years worth of data. That is absolutely fine. You can just see that that is, by eye, that's consistent. So there's no problem there. So you can see that for those of you that know statistics, slight offset, 1 sigma deviation from the first year of data, and then 3 years of data is just no issue at all. And then so that's the perpendicular direction, and the parallel direction that gives us a measurement of the physical density of dark matter. And 1 year of data, little omega matter is the physical density of dark matter. And then Planck has an error on this. Okay, so that shows you the 1 and 2 sigma ranges. And here are the results from 3 years of DESI data. That is the total, that's the complete set of data from the DESI instrument. There's a slight deviation here in this one bin, and it's not very significant. So there's no evidence for anything, any significant departure from the lambda CDM cosmology. So, so the hunt for a failure of this model, that continues. And amazingly, this shows a selection of experiments and satellites and things that are either being built or actually taking data right now. It amazes me that, you would think that governments would be interested in making sure that the trains ran on time and stuff like that. But in fact, governments of all political persuasions are really interested in dark energy. And so they've put lots of money into these experiments with the hope that we might learn something. And some discrepancy with the lambda CDM cosmology that will lead us to the next phase of understanding. To young people out there, there's plenty of scope for new discoveries. What I would hope is that, in a few years' time, somebody stands here and says, back then, the 2025 Shaw Prize winners, they didn't know what inflation was. They didn't know what dark matter was. They knew nothing. But here's what we've learned, and that there are plenty of Shaw medals, I think, left before we close the book on cosmology. So thank you.
Thank you, Professor Efstathiou. So now, may I invite Professor John Richard Bond to deliver his lecture.
Hello. Now I will tell you how the universe really operates. And I'm more optimistic than George about what we have learned and what we are going to learn. But I also, at some level, the mystery, which is fundamental, is also a detail. Because our understanding of the universe has been one of the major accomplishments of mankind, and it is an amazing thing, and I hope that I can get this to work. There we go. There we go. So I'm going to be typical Bond here, and my friends and enemies out in the audience will recognize everything that I do. And I am going to, as George said, talk about the Atomic Cosmology Telescope, but that's only one aspect. But I like this picture because it basically is the statement of a theorist who has worked with experimentalists saying eureka to the universe at large. And if there's a title, well, first of all, I'm a believer in imaginary time, and at that point you should jump up and kick me off the stage. But the title is Have Transport Will Travel, except that the fundamental ingredient is quantum transport. And then, as many people who know me, I'm an anthropologist. But when you think about entropy, entropy you think of as absolute randomness and associated with very large-scale thermodynamics because it was learned about with heat engines. But my contention is that the entropy is the most fundamental quantity in the universe, except that you should think about it as complex rather than just real. And what goes hand in hand with the entropy is that the universe is coherent, except for me. And the coherence is really the mystery. But it is you, believe it or not, you're all coherent because you are together as an entity. And I'm going to hopefully try and trip you to think about life, the universe, and everything in a different way. This is something that my good friends have seen me put up in place. It's not because I believe I'm Superman, but S means entropy, but it also means in physics action. And now I'm putting everything in terms of a very curious symbol, which you will all recognize, and that's part of my story. So I'm going to begin with a remarkable thing. I might say that Bond, the AI man, made this with artificial intelligence, and it combines what's called the Ouroboros, which is a snake that swallows its tail. There's my S symbol, and this, of course, you recognize as the yin-yang symbol, of whose basis is the Tao. And here we are in Hong Kong, and you all resonate, I hope, with the concept of the Tao, because the Tao is the universe, is my contention. So you see, I am not crazy, or yes, I am, but I'm crazy after all these years because from the very beginning, this is what I've been going for as a theory of fundamental reality. And what I did with George is associated with the flow of me from then to now. But I want to point out not just the depth of knowledge of this great Lao Tzu, but also I always point to one of the more remarkable things about existence, which is Pythagoras, 550 before the Common Era, was the quintessential theorist, like George and I are maybe not quintessential, but theorists. And what he said is that mathematics is not just the language of the cosmos, but it is fundamental to its understanding. And that is probably the most remarkable thing for humans to have ever decided. So you see, I'm going to try and trip you up here with interesting thoughts. He also introduced number, whole numbers, and it was essentially introducing the concept of the digital, which you all know very well. But the other thing that he emphasized, basing himself off of using a guitar-like instrument, lute, back at that time, is harmonic analysis, where everything is to be understood in terms of what we now think of as frequencies, if it's associated with time, and wavelength, or inverse wavelength, if we associated with space. So these all go together to make a theory of the universe, and my contention is that the Tao plays an extremely important role. And here we go a little bit later than the great Pythagoras, but before I say that, Pythagoras created a brotherhood called the Pythagorean Brotherhood, and the greatest physicists of all time consider themselves to be effectively within their own minds part of the Pythagorean Brotherhood. I would now say brotherhood and sisterhood, and that is defining how everything works in terms of collective efforts of human beings to try and deeply understand the universe at large, which is what our goal is. And so George and I are not just intellectual and friend brothers, but we are Pythagorean brothers. But then we move on to Plato, who played such a fundamental role as a student of the great Socrates. And he introduced something which is fundamental to everything that I'm also thinking about. You see, where is physics in this, you might say? Well, I'll get there. So the big idea, and of course the big idea is to comprehend the universe at large. He also called it the form, or the forms, and that you would try to understand everything in terms of the big idea. My contention is that you can never achieve the big idea. All you can do is make ideas with a small I that come together to make the big idea, which is basically the asymptotic possibility of the universe at large. So then I'm going to fast forward to somebody who has been, in my view, underappreciated as one of the greatest physicists of the last century, George Gamow, who also was one of the great jokesters of the world, which I love very much. So Gamow, well, he wrote a book that had an impact on me when I was quite young. And it has the most brilliant title imaginable, 1, 2, 3, Infinity. But it was infinitely associated with the concept of everything that could be understood mathematically. He also was interested in how the elements could have occurred. They claim that he did the Big Bang, but he never used that set of words. Quite right, because the Big Bang is not like a firecracker exploding. It is really revealing in a correlated way underlying space and time, and that's really the way to understand it, a fundamental instability in space that begins with things being close together and not talking to each other, and then they get correlated more and more and more. He introduced the word for this, elam, which is primordial stuff, and that's not just me playing with words. It's that was a terminology that got from ancient, not that ancient, ancient English, Old English, elam. But even before that, Aristotle, after Plato, but not so long after, also used effectively the same terminology. The most important thing from our perspective is that he predicted, and his students, that there would be a cosmic microwave background. And it was around the year that I was born, 1950. And George today said, I shouldn't be talking about age, but our whole treatment this afternoon was where he was dealing with his age. Well, CMB at 75 is being talked about today with Bond at 75, when I formed in the Platonic sense. And Efstathiou is a youngster, and he formed 70 years ago. And so we have been trying to play the game of Gamow, where Gamow tried to tell the full story of the evolution of the universe from the beginning to the end, and paid special attention not just to the early periods of the universe, but how you can then understand the formation of the Earth, the formation of life on Earth, et cetera, et cetera. And that is the great cosmic story that we are all trying to do as a collective, as human beings. And so I use the Ouroboros, and I've used it since the early 90s in this rather cartoonish sense. But I use the skin of the Ouroboros as a measure of time. And so the concept is, when Lao Tzu formed, and others, he had this cosmic eye looking back at all of past history, except they didn't get to look back at much past history because they didn't have the knowledge for it. But we now think that we can look along the whole train from here and now all the way back towards the beginning. And so I will be trying to flesh out these concepts as we move along and how it's related. And what it was that the Shaw Prize for George and I was explicitly giving us credit for. So when I first started this game, we didn't know what the beginning was, and we still don't, as George emphasized. And so the way I treated that was to say there is a cosmic dragon at the beginning that breathes a coherent universe from it. And, you know, more or less, that's still the best we can do. So we have the cosmic dragon here, and of course that's quite appropriate to an audience of people who are of Chinese extraction. And the universe then evolves. This is the inflationary phase. But the most amazing thing about this is what you need is coherent time to make this story work. And coherence and time, and let's remember that I put this as the fundamental aspect. And so George talked about the theory of inflation, and that is coincidental with the emergence of something that we call time. And then tick-tock, 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 all the way to now. But before then, and we even do theories about this, it goes tick-tack, tock, tick, tock, tick. That is to say, there is no coherent time, and so you need that to tell what the future is going to be and how things develop. And the expansion of the universe is, in fact, one kind of measure of that. The thing that George and I were most cited for was the period and the calculation of a period when the photons went back and forth and back and forth and back and forth, and it was not transparent. And then there was this period of let there be light, sounds familiar, and then the photons started to propagate freely to us. And the way it works, as I think everybody knows, is that you begin with a wavelength which is short, and the wavelength stretches out as space expands. And so what started when the light got released from being back and forth to now is that it started as red light at this period, which is 0.38. Think about this. We know this number really well. 0.38 million years after whatever happened here. And it became a coherent flow, taking to us all of the information that occurred at that period, when the universe was much simpler than it is now. So this is when the microwave background was released. But there are other things that are near and dear to me. A cosmic neutrino background. And George talked about the neutrino background of the universe and the possibility that it can have mass. And we now know that it does have mass. It's just not a really big mass, but it is a weird mass because it's enough mass to be the equivalent of all of the stars in the visible universe. Isn't that weird? My own view is that Mother Nature is really strange for not having chosen to make it the dark matter, and yet to make it so interestingly large to be all of the radiating light stars in the universe in terms, and that got released at about 100 seconds from the expansion beginning at when the universe was condensed by a factor of about 1 billion in scale. The ingredients when the photons were released is photons, electrons, and nucleons, which we call baryons, dark matter, and that was fundamental to everything that George and I did. There was microwave background before dark matter in terms of us intellectually knowing about it, and then the dark matter changed everything, and it made everything clear. But Mother Nature could have pulled the rug out from under us, but she decided not to, went, yeah, that's a good model. And so the model that we've got now, the one that George talked about in detail, is the model that Mother Nature decided to gift us with. And at the same time, there are these mysterious weakly interacting particles that are coursing through you now. The cosmic neutrino background is passing through you as we speak. And you can even detect the photons from this early time. If you turn an old-style television on, it's part of the snow noise on that television. So these are real. And we know from our microwave background studies that they're not just real, but it's absolutely required to make the models work. And that is an amazing result and accomplishment that came from the microwave background. But then, as the universe expands, the very first stars form in very tiny galaxies. And then, as time goes on, they cluster together and get bigger and bigger as galaxies and form the cosmic web, which was the other thing that the Shaw Prize pointed to, the work we've done on fleshing out the story of the cosmic web and its development. While the cosmic web was developing, the Earth formed. So pretty interesting. And it's a little bit about halfway in between. But the cosmic web is something that started when the first stars form in terms of its structure and continues to now. And the remarkable thing is that as we look out into the universe, for example, with the James Webb Telescope, looking essentially to the first galaxies that form, it's all cosmic web, cosmic web, cosmic web. It looks different at every time, but it's all cosmic web. And it follows absolutely from this period. I could wax eloquent about how all of this works with this yin-yang symbol, but basically let me just say that universe, which is this whole, is split fundamentally into signal and noise, stimulus and response, which you're probably used to thinking about, particles and holes, which are more mysterious and I won't have time to get into, questions and answers. How about that? If you question the universe comes back with an answer. And it's symbiotic, and this sort of represents that there's a boundary between questions and answers. And it isn't just that it's on some large scale or on some small scale. It's on every scale, and it's tightly coupled, questions and answers. That is the fundamental nature of physics. And that is part of the thing that has been our intellectual enterprise to try and make that story go. And whose basic idea is this? Lao Tzu. It's the Tao. The Tao is the united. And then what the Tao Te Ching talks about is the development of the myriad. And what that means is that when you are together, it's fusion. And when you split apart like this, it's fission. Fission, fusion, fission, fusion. And so that is a fundamental aspect of the universe. And I've wanted to study and do study all of those things because that is the language of the universe on all scales, which gives us hope that we can understand this unimaginably early time in terms of these basic concepts, which in fact, the basics of particle theory is that for every charge, and charge can be energy, charge can be momentum, or charge can be electric charge. And the other side is field, charge, field. Stimulus response. That is the language, and you know this if you've done any physics at all. You know that it is this coupling which is associated with what we call the Lagrangian, but it's also associated with the imaginary entropy in ways which I won't describe. Cosmic web is one thing. So now the thing that is my passion is working out the cosmic superweb. So, you know, super web and such the superweb. But what the superweb is all of the fields, all of the charges, all working together in ways that make the universe evolve in the way they do from the beginning to now. It's just that when it's the cosmic web, it is basically saying that it's defined by X, Y, Z, and time. 3 positions or space variables and time. Here, we don't know how many variables there are. Another way to say it, we don't know how many dimensions there are. And so dimensions can be a very large number at early times, and then the important dimensions are the ones that had the expansion from this period to this period, which is space. 3 space dimensions. See, I'm not going to get very far because I can't resist. So I'm going to say a few words, and then I'll probably leap to the last thing because I'll run out of time. I don't know how much time I do have.
15.
Yeah, okay. Here we go. Okay, so everything that you heard, it sounds like it's metaphysics. Knock out the meta in metaphysics. There is only physics. It is all physics played out. Physics defines life, the universe, and everything. And how do we know that any of this is working? It is because of the Pythagorean concept that mathematics is the key to understand the universe at large. So there is only quantum physics. And another way to say the same thing is there is only quantum information. And because there is only universe, it is quantum cosmology. Now this is, you might say, that a little bit of hubris, that what George and I and my good friends who work on this, quantum cosmology is what we do, and they're the most important thinkers on the, but that's thinking about everything. I was going to give a riff of the person that is really amazing, Albert Einstein, but everybody knows that, so I don't have to say anything about it. But what I will say is that this is the year declared to be the year of quantum science and technology, and everything is quantum. And many people don't or did not understand it. But in fact, quantum is at the heart of what George and I did, because he used the words polarization, and polarization is spin, and spin is quantum mechanics. And when we transport things, we transport a matrix that includes the information on the spin, and the photons have spin. And so wherever I said it, here we go, we transport not an occupation number of different states like the photons. We actually transport an occupation number. And we transport from then and there, some initial state, to here and now, a final state. And George emphasized we didn't know what the initial state was, and he said the miracle there was the development of inflation. And so it is true, but there were many more miracles that came along in physics that allowed us to try and break through to understand a little bit more about the initial. The remarkable thing is that final, with the Planck satellite and ACT and other things, allows us to interpret the initial. Anyway, if I go on about this, then I won't even get to the last slide. However, the one thing I will say before I go on is that many people, including George, like the idea of multiverse. There is only one universe. But within that universe, there are many realities. In cosmology, we call them realizations. And so when George was showing you the numerical simulations that developed into the cosmic web, what he was doing was creating a realization which he then propagated forward, and he did it with my good friends here who are in the audience, and we have done much work since. And it illustrates that you make a reality and you propagate it to see does it agree with data or does it not. Fundamental to this is probabilities of realities, and that's what quantum mechanics is all about. So, and the other strange thing about the quantum world is that realities interact. So that if you try and concentrate, this will sound very mysterious, concentrate realities too closely, they essentially repel each other. The way you've heard about this before is the uncertainty principle. But that's not really understanding what's going on. It is that there is a wave aspect, and the wave aspect is as fundamental to what we call the particle aspect, and that is the deep mystery of quantum mechanics. And it is not the way people usually think about it, but it is that an example, well, I won't get into the example. The fundamental processes in the quantum world is what I referred to before: fusion, fission, fusion, fission, and then something else. Something really weird that is only quantum. It's called quantum tunneling. Quantum tunneling experimentally won the Nobel Prize this year. So this has been recognized as one of the great accomplishments of humanity. But who came up with quantum tunneling? It was George Gamow. He was the first one to say how important the possibility of quantum tunneling was. And the other aspect, which is fundamental, is coherence, and you've heard me use that word before. And what is the opposite of coherence is decoherence, obviously. And that means that it is very difficult to maintain coherence. And that is the reason that, I'm sure you know, that quantum computing is so difficult, because it requires phase locking or coherence to be maintained over time, and decoherence is there. But the universe at large also decoheres, and I won't say more about that. I'll leave that as a mystery. Key to everything that fits here are what are called transfer functions, or we are now talking about as response functions. And it isn't just the sort of thing that George fit, Carlos, in order to begin the first cold dark matter simulations into nonlinearity. It is response functions are everything. And it is an industry at CETA that we are trying to calculate response functions for everything associated with the cosmic web, because from that we learn about the universe at large. And if I have time, I'll say something about that, which means I better know how much time there is. Great. Okay, so here we have Mr. Gamow and cosmic superweb. Cosmic superweb is intimately associated with a theory called supergravity. In 11 dimensions, 2 of which I interpret as time, one of which is space-like, and then there are 9 space dimensions. So that is what is supposed to be possibly the theory of everything, sometimes called M theory, but it's also matrix theory, and matrix is fundamental to quantum mechanics, and it's all intimately related to superstring theory. And I'm sure many of you know that there was great hope that superstrings would be the fundamental theory behind all of reality, of which all of the inflation things would follow. And while everybody else is abandoning it, by cosmology, I have grown to decide that that is what will underlie the full theory. So I am now an aficionado of superstring theory, and that you start with 2 dimensions, and then they interact in a way that makes multiple dimensions of space, and that's the way all of physics is developing. And it's really a matrix theory, and matrix is what you do when you transport from then to now. Okay, I was going to have to quickly run through this, but this is a description of my beginnings at Caltech. I started at the University of Toronto, graduating in 1973. Have transport will travel, you see that was part of my title. And I was very struck by a project I did then about superfluids, which you may know about. They don't have viscosity. And what they describe is a collective quantum thing. And what I wanted to do is to try and see, are those ideas the interconnectivity of things in the universe? And so it led me at Caltech to do all of the work on neutrinos and nucleons, which make up nuclei, many body physics. And it is very deep because neutrinos interacting with matter in the medium is completely understandable as neutrinos interacting with collective phenomena. And everything in this room is a collective phenomenon. Then Berkeley was the next step, and that's where George and I started our work, and it was triggered by the neutrinos. And then went to Cambridge, but Stanford for before that. Then I had a little excursion to Cambridge, 82, 83, and George and I started the CMB calculations then, and we'll see the very strong role that Alex Zale in the front row here played when I show you the next figure, which will be very personal. And so when I was at Caltech and then moving on, I was dealing with 5 decades, or have been dealing with 5 decades of cosmic neutrinos and 4.5 decades of cosmic photons. And we are in quest in all of these cases for not just what we now know as the standard model, but we're always looking for the beyond the standard model, the new physics that we have yet to discover. So I'm going to point out a few people here. In 1980, at the Institute for Theoretical Physics, in the very first program that occurred there that was associated with Hans Bethe, I gave a talk, Entropy, Neutrinos, and Supernova, and believe it or not, I actually taught Bethe some things because he was one of the great physicists of all time. There he is there, and I was infinitely pleased to become awarded with the Bethe Prize of the American Physical Society, and gave a talk with this title, guess what, Entropy in a Coherent Universe, in 2024. But just to show that entropy has been part of my being for all of these years, I riffed off of the 1980 talk at a meeting in 2020 at the Institute for Theoretical Physics, then with the name Kavli in front. And it's entropy, phonons, and phase transitions, which was all about inflation. And I think it is a deep idea of inflation which is that we can really understand what is going on. It's about the cosmic superweb. So George is the pessimist, and I'm the optimist. This was my thesis advisor, Willie Fowler. If you think he looks like a laughing Buddha, he was. An amazing character. He worked with Fred Hoyle and the two Burbages, and they wrote the tale, along with others, of how all of the elements, heavier than helium, arose in stars that blew up. And you are all the products of that, as you know. And you know everything that I'm saying, but I hope that you might be looking at it in a slightly different way, according to the language that I'm using. This is Bob Wagoner, who worked with Willie Fowler and Fred Hoyle in 1967, not too long after the microwave background was discovered, to do what was the definitive work that Gamow had started, Big Bang nucleosynthesis, where the key thing is the elements of hydrogen, helium, some lithium. That's what you can make in the Big Bang. That's what led Gamow in order to create, to predict the microwave background. This is Jim Peebles, the very first Shaw Prize winner, and he also worked on that subject along with many others. And he's Canadian, so therefore we know that whatever he does is cosmic truth. This is Niels Bohr. Whoops. This is Niels Bohr, and this is John Wheeler. And I'm not going to have time to play that much with them, except that let me say that the theory of fission was Bohr and Wheeler. And the theory of fusion in stars, for which he got the Nobel Prize, is beta. Fusion, fission, fusion, fission. That's the story of the universe, except for quantum tunneling. We had a great meeting at Durham to celebrate a birthday party of somebody that I worked with George and with our good friend Nick Kaiser, who we were also celebrating. And I was delighted to find and tripped over that in 1947, the great Niels Bohr, who basically was at the heart of the development of quantum mechanics, made a coat of arms. And look what he put in the center of the coat of arms. So he was coming to the same concepts as I was, different in thought, but that yin-yang was the way to think about the development of phenomenal reality. You will see in the next thing, maybe I'll go to it, is with Nick and celebrating him, I added this little piece. The ideas we had, the parties we had. Because the way I find our subject works is that we try and do great things together, and we do it with deep friendship. And George is a deep friend, Alex is a deep friend, even Carlos is a deep friend, and Simon over there, and so many others in the audience. And I think that's one of the things which I find, they want me to wrap up. So I knew I wouldn't get very far, because once I get going on this, it's a joy. This was to describe the history of the microwave background work that we did, and who the great people were before, and that we encoded polarization in it. That's our good friend Nick Kaiser. And we also did a lot of work with Jim Bardeen, who was in on the ground floor, not appreciated, of the microwave background. And then there's Alex Zallet here, who worked closely with me, and then also on many different projects over time. And so I put these captions Jim Peebles said, reconsider lambda. And this was in the 85-87 period, and said, this is a possibility for the universe. And I won't get into the other aspects of what he said. And this is me, looking much more handsome than this guy up here named Efstathiou, and defining the nature of the dark matter, but also saying they could be something else. And black holes are one thing, and black holes is dark matter. It's just that it's not that much dark matter, but it's there. And this is Martin Rees, who is so iconic, he deserves to be a statue, and worked on something else which is quite remarkable, is that the universe had to work to make us. So there are many possibilities that could occur, and the anthropic principle is what defines that it's habitable for us. And so just by that thought, you can place a constraint on what this cosmological dark energy is, because if there's too much of it, the universe expands so fast that you can't create galaxies, you can't create Earths, you can't create human beings. I will have to end on a picture of people. This was at a party in Berkeley when we were doing our work. This is George at the party. This is me, you know, the deep thinker. But you might also note that there's something in my hand of spiritual form. This is Joe Silk, who is very working with us a lot. Alex, I should have been able to get a picture of that time. I really wanted to get a picture of Alex with as a rock star, because he was before he became a cosmologist. This is the Jim Bardeen that I talked about. And there is this famous meeting in Santa Barbara in 1984 where we all got together, and the Institute for Theoretical Physics in Santa Barbara still to this day considers this to be the most important meeting they've ever had, because that was the birth of our ideas. So George and I did the cosmic microwave background. It was passed over to Davis, White, and who is this guy? Frank. And this is our good friend Bernard, and guess who that is? George. And of course, with the more spiritual considerations, that's Bond. And there I am looking really cool and very handsome in Berkeley about that time. I mean, look at that. He's got the shades on. I was going to go through a history that led to the ideas of the cosmic web, but I do not have time. But I'm going to pay homage at the end of this to Jim Bardeen, who died, sadly, in 2022. But with him and Nick Kaiser, we did what was recognized as part of the Shaw Prize work. It was a paper called BBKS, which doesn't mean anything to you, but it was applying statistical ideas to how structure formed in the universe, and it provided a language to understand what one was seeing in all of these dark matter, nonlinear simulations that George described. And so it gave the framework to understand things. And then with my good friend Lev Kaufman, who sadly died in 2009, we extended this and some ideas that I had worked on with other people, which I won't get into. We came up with the cosmic web. And what is the cosmic web concept? The cosmic web concept is, you've seen all the microwave background stuff. You haven't heard the microwave background. That's what it sounds like. Okay, I'm going to blow you away here, because I can't resist showing you what happened when one added the Atacama Cosmology Telescope data to Planck. So on this side, it's Planck. On this side, it's the Atacama Cosmology Telescope data. And you see that as it sweeps across, things that you can't see in the Planck data start to come out. These are little sources in the sky from which we learn a remarkable amount. And so this is the story of increasing resolution, which allowed us to get remarkable results. That's polarization, which is even more dramatic. And then George emphasized this figure with the very small error bars on it that was derived from Planck. This is the data of Planck, and where this ends is this line here. And all along here is the ACT data. And look how far it extends to very, very small resolution. But that's not the real story. The real story is how well it does in this other thing called polarization. And so here is the Planck data, which was fantastic. It was a great polarization thing, but look what we did with ACT. Isn't that amazing? And so I probably will go to the last slide. No, don't worry. We'll get there. Cosmic Web. Cosmic neutrino background. My thesis advisor would be very proud by what we did. And here I am. They were trying to make money off of us at the University of Toronto, so they took this picture of, you can think of it two ways. Cosmic Explorer is one, Space Cadet is the other. And so, you know, looking up and all that stuff. And I described some things that I'm really excited and working on now. But what I'm going to end on is the last slide that we showed the 16 to 18 years old this afternoon at the Space Museum, which was advice. You know, we're supposed to be wise, George and I. My random advice was basically get technical, compute things. But the other was, how do you deal with existence, with the possibility that artificial intelligence is going to take over and we're going to become irrelevant? But I described the yin-yang, and on one side is reservoir of information, and on the other side is the system. And so the humans are the system, and the reservoir is the information that the artificial intelligence gives. And so it is that interplay, which I believe can be our future. It is possible that artificial intelligence will take over, but then it will not be wise. And my final advice to the students was question authority, except if it's George and me. And that you belong to the universe. The universe is the Tao, and you are the system. And the rest is the reservoir, and artificial intelligence plays with the reservoir. The theory of artificial intelligence, believe it or not, I believe, and I'm working on this, is really the theory of the cosmic web. Hard to believe, but it's got all of the ingredients. And so what we can teach them as cosmologists on how to think about artificial intelligence is, I think, profound, but I think I'm probably the only one who really believes that. But it's an important problem for us to understand, which is the basis of why artificial intelligence is working. And on that note, you will be happy to say, now you see they're all lined up, ready to pull Bond off the stage. And so I will self-pull myself off the stage. But thank you for listening to my not metaphysical thoughts, but physical thoughts, because it's all based upon data, our data in dealing with the universe at large.
Okay, thank you, Professor Pon and Professor Efstathiou, for the enlightening lectures. We will now have some time for a Q&A session. So I encourage the audience to take advantage of this opportunity to ask your questions. It is a unique opportunity for us to deepen our understanding. Please don't hesitate to share your questions and let us sit down first. And if anyone want to ask questions in Chinese, I can try to translate it.
Don't expect us to answer in Chinese,
Okay, we have.
unless it's about Lao Tzu.
Hello? Do you think we need bigger, much more, do you think we need a bigger telescope or much more expensive equipment than James Webb?
The question is,
Do you think we need a bigger telescope or more expensive equipment than James Webb to help us to understand the universe?
the telescope size is extremely important.
Okay.
So the ACT telescope is substantially bigger than the Planck telescope. But the key thing that caused the transformation is the sheer number of detectors and the technology behind that. What you don't want to do is to get a cold when you're working on this stuff. But anyway, so big is better, but new technology is what's made all of the difference to our studies.
Could I make a comment?
Of course.
Yes, okay. So Dick, in his talk, said that he was the optimist and I'm the pessimist, okay? So to reinforce that comment, yes, we need more equipment, more projects, bigger telescopes, but nature also we have to be lucky for nature to reveal more secrets about the universe. We could be here 50 years from now, and it's lambda CDM, and we've detected no evidence for any departure from that theory. So we have to be lucky. It's not just equipment. We have to be lucky that nature, something new is detectable.
Okay, we have a question in the back.
Thank you very much for the interesting lecture, especially on this on sharing of personal life of a Shaw Prize laureate. My questions regarding the universe. Recently, there are more evidence showing that the universe is like spinning and rotating, together with the fact of singularity and the fact that we cannot see beyond the cosmic background. There is a proposal that the universe is actually within a single black hole. Do you think that's the case? If that's the case, what will Hawking radiation look like for observers like us inside the universe? Thanks.
Right.
You want to do it?
You go for it.
So he gave me the
could
toughest question,
I
right?
could comment on one
So
aspect of that.
Here is my idea. What the expanding universe is, it's what is called a white hole, not a black hole, because things are spewing out. A black hole is when things come together. They're both associated with instabilities, and what happens is the universe expands, you get these pockets of collapsing things that creates the cosmic web, and within that, you collapse and make the black holes. The natural evolution under gravity is to make black holes and void. There is the central object, and then it deals with the issues of entropy by radiating that out into the void. And so it is natural to get a lot of black holes. And the structure of the universe is effectively infinitely associated with what is in it. It's sort of Hawking radiation, but it is occurring at the horizon scale of the expanding universe, and that condenses out the fluctuations that ultimately give rise to all of the galaxies and everything in it. So it is intimately related, but it's not exactly Hawking radiation, which is associated with radiation from effectively the surface of black holes. But there is an effective surface, which is the scale of the horizon, which effectively radiates out information, which condenses. And that is the origin of all of the structure of the universe. And if that sounds wild, it is, but it also is.
Well, I mean, so there is a big puzzle with dark energy, because if dark energy is a cosmological constant, then there is an event horizon. So we're surrounded by an event horizon. And whenever you have event horizons, that causes problems for physics. And that's one of the reasons why people are skeptical about whether the dark energy really is a cosmological constant.
Okay, thank you. There's one question here.
This is about like the lambda CDM model. So how are the anomalies actually addressed in this model? Like, are they like explicitly validating like how this whole thing works, or
What did you refer to?
like the
Anomaly?
Hubble tension and also like the S8 one?
He's going to beat up those people. Go ahead, George.
So, well, I don't believe that there's strong evidence for either of them, for either of these tensions. I mean, the S8 tension, I think that the pendulum has shifted now, and that a lot of people now think that the issues with gravitational lensing were caused by systematic errors in the measurements. The Hubble tension, I think, I said in my talk, there are two groups that have been measuring the Hubble expansion, the Hubble parameter, using very similar techniques, and they've been doing this for a long, long time. So both groups have a long history of experience at these measurements, and they disagree. I mean, the disagreement in the value of the Hubble constant is very small. It's 3 kilometers per second per megaparsec. One group puts an error of 2.5 kilometers per second per megaparsec. The other one puts an error of 0.8. Now, personally, I think that the error estimate of 0.8 is ridiculously small. Okay, and if the error is really a more realistic error is 2.5, most of the problem goes away, and then that would leave the difference of 3 kilometers per second per megaparsec. So I think really those groups need to sort out their differences. Okay, and then we can, the rest of us. I've written papers on the measurements. Okay, and I told people at my institute, if the thing is, it's such a polarized field that it's very difficult for an outsider to contribute usefully to it. And so what I told people at my institute was that if ever I showed signs of writing another paper, they were to tie me to the pillars in the Kavli Institute until the feeling passed, like Odysseus and the Sirens. Tie me and let the feeling pass, and don't let me write another paper on the Hubble constant.
Can I add to that just for a minute? So there has been a constancy of one of the groups in their value of the Hubble parameter. But what happened is they completely changed their results. It's just that one set of errors grew in one direction, and another set of errors grew in another direction. And so miracle upon miracle, it came out to be the same Hubble parameter, and you should be skeptical if such a miracle occurs, which is essentially what George is saying. On the other hand, we don't know who's listening in this, so we have to be very diplomatic.
Okay, thank you. So in view of the time, I think we have time for only one more question. Maybe we'll take one from over there.
Thank you for the amazing talk. I just want to ask a question, because from what I heard and what I understand, I think most of the points in the universe are quite coincidental. So do you think there is a creator behind all of these things, or what are your opinions on it?
Up to you, George.
I don't do God. Okay, so.
I do.
Oh, okay, so Dick can answer the question.
Cosmology has all the answers. Physics has all the answers. But you may realize that the theory behind the Tao is effectively a religious theory, and I was extolling its virtues as the fundamental underlying thing. And if people realize that, maybe religion wouldn't be so polarizing as it is now, because it's all the same thing. It's the universe operating. It's just that sometimes the universe makes particles and sometimes it makes holes. The holes seem to be negative, but it's all in the eye of the beholder, and it's all a process. It's a dynamic process, and that is the context in which religion should emerge, and we have learned so much that maybe we can make a grand unification of ideas in which all of the polarizations of the different doctrines are transcended. And of course, what would transcend it? It's the theory of physics. Right, Carlos?
Absolutely.
All right.
You see,
Carlos and I agrees with me, then you know that we're on the right track.
see, my colleague here doesn't just want to make a theory of the formation of structure in the universe. He wants to solve world religion as well. You know, so.
Absolutely. It's the same problem.
Don't limit your ambition.
On that very interesting note, thank you for your wonderful questions, and I hope you take home valuable insights from today's discussion. Now, can you please stay for the souvenir presentation? So for that, may I invite Professor Quinton Parker, Director of the Laboratory for Space Research, to present souvenirs to Professor Bond and Professor Efstathiou.